Hello, this is Joshua Goossen. I am a student at Georgia Tech in the Georgia Tech Online Master of Science in Computer Science program. I am an information security specialist and have had some experience in the industrial systems area, working for different manufacturing plants. This particular course I'm providing a presentation for is CS6263. It's a cyber physical security class. And the paper we're looking at is optimal control versus safety red lines, the Internet of Things, safety via micro-policies. It's a paper that was put together by Saman Zonouz of the Electrical Computer Engineering program at Rutgers University, and Robin Berthier worked with him from the Information Trust Institute at the University of Illinois. Why is this particular paper of interest? I felt that, at least to me, it was interesting because I think we're seeing, I think we've all seen different applications of the Internet of Things, whether we're looking at our own Apple HomeKit or our own local, home area network, or whether just recently I was privileged to see a presentation of drones actually at Walt Disney World. So in our daily lives, we come across these Internet of Things applications, but also behind the scenes, if you consider Amazon, we'll go into the next slide, they actually have a large number of robots that actually work together to efficiently sort and transport products that we receive in our homes probably every week. In addition to that, there are military reconnaissance systems and even agricultural systems that are in place that provide services simply more efficiently. The downside is that while these Internet of Things systems become more efficient and bring us increased value into our lives, they are also opening up new potential attack surfaces. And this particular paper makes it clear that there have not been anything like a Stuxnet for these Internet of Things systems yet, but it is a potential. And clearly, as more and more systems go online, the risk increases. And I think that it really is what is highlighted most by this paper, is that essential conflict between security and convenience or efficiency, because most of these systems are being driven by cost optimization, but the reality is that often also cutting costs can result in safety and security concerns. I think the other key relationship here is that at least I want to highlight is the relationship between safety and security. And I think this goes back to the history of each, where safety has historically been more of an engineering consideration. We're talking about safety valves and safety systems at a manufacturing plant or within maybe a cruise ship. Those are conversations that engineers would have. But now, in an information security world, safety and security have become one and the same, where particularly in cyber physical security systems, we're discussing, well, what happens if somebody is able to trip that safety valve, or maybe to turn off the safety system now remotely because we have maybe the cruise ship safety system is now online. Um, so I think that's another, if you know, to really highlight some key relationships, you're looking at the relationship between safety and security and convenience, and it's a theme throughout this paper. The paper also makes it a point to discuss both accidental and adversarial events. And that's important because you have kind of the Homer Simpson dilemma, you know, but without making too much of a fool of, you know, out of our operators, the reality is humans make mistakes. It's possible as systems become more complex that simple human mistakes can result in large, unforeseen tragedies and consequences. What was nice is that the paper actually referenced several articles, and so I looked some of those up. And in fact, you know, they tied in some actual nice examples, which I've already mentioned. Amazon already has these little orange robots. I guess the pictures are very useful that move inventory around, make it a little easier on workers to, you know, it really just takes the hard work off of the workers' backs and provides products to them to then load into trucks. But the concern here is, you know, how do you actually prevent these robots from being used maliciously, potentially damaging all of Amazon's inventory, or even potentially, you can imagine these things potentially harming employees if they were to drop a shelf, say accelerate a shelf into an employee. And potentially they have safety and security mechanisms built into these inventory systems. But I mean, that's an opportunity as these systems become more in use, and those of us who are in information system development, these are things that we have to think about as we're building these systems. Additionally, they had some articles on flying drones and how they're being used in agriculture and the military, as well as some home network systems. So they first start really by talking about the problem, and the problem is with the traditional and the existing regime, which it comes out of, you know, these monolithic combined control safety architecture. So if you imagine really just a manufacturing plant, and we see that metaphor a lot in cyber physical security coursework. If this manufacturing plant has some solid walls and all the insides, it's almost like a cell, all the insides of the cell are protected by those walls and maybe the security guard and maybe the security checkpoints. But once inside, all of that detail is exposed. So the assumption in that traditional manufacturing plant model is that you know, physical security is just enough as it is, and you're not going to have internal threats or internal components that are going to be compromised. And clearly that just is not how the world works anymore. That made sense before information systems made everything so well networked and fluid. So the traditional systems, effectively, if you put them against an adversary that's trying to bring them down, they're going to fail quite easily because those systems are, we're talking about microscopic information systems. Now those systems are very porous and the attacker can get in through even radio waves or wide area or wireless networks potentially. So this traditional castle building and way of drawing up lines to separate the world no longer works anymore. You have to think more in terms of adversarial views. So the proposed system does just that. It adds an additional layer, logical layer. This is a safe SIM layer. It just happens to be what they refer to it as. And you can think of this as a police officer, if you will, that just basically enforces policies and makes sure that the actions that are taken fall within the lines of what are appropriate and what are predefined by the manufacturing plant or whatever system we're evaluating. I think in this case they're looking at a power system. They were looking at a power system because they're building a prototype for a power system. Those of you in information security probably recognize this already. This is something like what you might find in older Windows operating systems, where they might verify certain actions. So there's a security layer that was separated over time and within the operating system. They separated out the security model, and I'm sure that varies across the operating systems now, exactly how they do that. But for the most part, I think that is becoming a bit of a standard. This is also the TCB model, and this is just a giant TCB metaphor. That's what they did. They took the TCB model and they tried to apply it to cyber monitoring and control at a larger scale. The model calls for 3 components, and the paper doesn't get into too much detail on these. I think it's part more of their prototype that's outstanding. They get into micro-policy enforcement. It seems that applies more to the administrators or the system admins. Control action checks on the controllers, and the sensor checks on the monitors. And so effectively, before actuation happens, or before sensors can provide a view of the world to controllers and monitors, they have to pass through this safety system. Now you might say, well, really the system's not secure. You could have somebody just take the safe SIM system potentially, and that might be correct. But I think the benefit here is that in most cases you're dealing with attackers that gain access either through, the internet. Maybe the attacker, in the case of Stuxnet, maybe the attacker got something into a USB that then got transported into the network. That's a possibility. Maybe the attacker, it's probably more likely that the office that controls the manufacturing plant has internet access, and somebody installed the wrong software, and an attacker now has compromised the office up in this corner. Or you can imagine attack scenarios where that are more likely that maybe there's a remote control box or system, and the attacker is able to compromise some of the sensors or some of the logic controllers inside of the control boxes. That is more realistic of an attack scenario based on just what we've seen with Stuxnet and other cases. And now, effectively, what this layer does is limits the attacker. So if they do actually are successful at compromising an actuator or a sensor or a monitor, they're going to be stuck at that layer. And these policies are going to not let them change the voltage sensor or the current sensor. Effectively, it limits their action, and they're closed in to a particular system because of these policies. That doesn't prevent them from potentially using underlying protocols to then take over these other components, but it does add an additional layer of control. And I did add some of my notes. My thinking here is, I don't know if this is really realistic from the standpoint that TCB was really developed, as far as I know, TCB was developed more for, say an individual hardware system. So we're talking about something microscopic, and maybe that individual system costs, hundreds or thousands of dollars. But what I'm questioning here is whether or not this system can actually be applied, or the TCB system can actually be applied to something as large as the nation's electric grid, where now we're talking about thousands of systems that cost billions or potentially trillions of dollars. And at least for me, it's questionable as to whether or not we can apply that same type of control. While clearly logically we could, how much would it actually cost to change all of those components? And that's just an unknown for me as somebody who knows nothing about the electric grid. And I think really, for the most part, the paper breaks off into just kind of, after they propose the solution, they kind of list out how, at a very high level, how they would intend to implement pieces of this control. And I think here's where I get the feeling that there's a lot of definition that needs to be done. Their prototype, I have to check and see if it's actually been completed. Their prototype will be very telling as to whether or not this is a very high level concept that is just not actually actionable, or whether or not they can actually produce something that's of value. At least I would be questionable. It would be questionable to me as to whether or not they could even scale it. So they talk about here for the proposed solution, they propose to further separate the plant control and the monitoring, and they recommend a few of the different ways to do that. First, they want to monitor the, let me skip to here, they want to monitor the embedded devices for unsafe actions. They want to have increased security built into the SHM safety systems. I think this is talking to more of the security versus safety kind of paradigms, which have begun to merge. And I think you're seeing that in their proposal at the very least. And they want to include a trusted safety verifier module to verify actions do not violate the safety requirements. And they also recommended linear temporal logic to verify safety criteria. And again, this is high level. My feeling is that they've taken a collection of maybe white papers and other studies, and they're kind of forming a strategy as to how they can implement this very, very high level solution. So will it work? Could it work? Is it really realistic? I mean, these are all questions that are still left on the team to be answered. And the paper closes out by talking on really embedded micro policy enforcement. So in addition to actually formulating a solution that involves these components or these kind of guiding principles, they are hoping to include these things. So policy enforcement, making sure that they are distributed. It's kind of a working strategy, so that they would distribute policy enforcement across IoT nodes. It's not clear as to whether or not they intend to have, let's say, safety-specific Internet of Things nodes, or whether or not they would use the Internet of Things nodes. In their case, the prototype is looking at an electric power grid. So again, it's not clear as to whether or not they would reuse those components or exactly how that would look. The paper just really leaves that out. So theoretically, it could be either case. They propose having the nodes work together to cooperatively satisfy safety requirements. They don't propose how to do that. It was just my feeling. I was a bit unsatisfied to see a point like that. It's just too, for me, it's too much of a high-level requirement or goal, but I don't see any indication as to how they actually will meet that objective. And finally, they talk a little bit about the prototype, but they don't provide a lot of detail. So I guess overall, the conclusion, of course, is that this is a continued work in progress, and I think really that's where they leave off overall. I think it'd be worth a check, and maybe I'll add some posts and follow-ups. It'd be worth a check to see where this leads and whether or not their prototype is actually successful, and then really to continue searching for other similar papers for those who are interested on similar strategies and the effectiveness of those strategies at ensuring control is both optimal and can ensure safety of systems. And that is my presentation. Thank you for those of you who came across this on YouTube for taking the time, and thank you, of course, to the students and professors at Georgia Tech who take the time and review these materials within Georgia Tech. Thank you.